Hello everyone, Kazi here, and today I want to talk about a very interesting aspect of quantum mechanics, which is that we are very well aware of the fact that one of the features and characteristics of quantum systems is that they exhibit this property of quantization, which means that there are only discrete set of values that all of the dynamical variables such as energy, momentum, angular momentum, and so on can take, right? So this is a very important feature that is ubiquitous throughout all quantum systems. So there's a very natural question to ask preceding these observations, which is that why is there quantization in quantum mechanics? What is the origin of the quantization in quantum mechanics? So what are the principles that governs this behavior, right? So what I want to demonstrate to you is that quantization in quantum mechanics is actually a consequence of normalization. So I would like to explain to you how that normalization causes quantization in quantum mechanics. So I want to take a simple example of a half harmonic well. So imagine you have a half harmonic well and you have a particle that is confined inside of it. So the potential here is infinite, the potential here is 0, and the potential here is some V0. So the height is V0 of the potential. So now if suppose you have a particle with an energy E, so first of all one would expect that naturally, because Schrodinger's equation describes quantum systems, so quantization might be a natural consequence of the differential equation itself that is governing these quantum systems. But that turns out not to be the case. In fact, even the boundary conditions which we will impose here are not sufficient to give us this feature of quantization that we observe. Okay, so let me convince to you that that is indeed the case. So we know if we solve the Schrodinger's equation, in this region, say region 1, the solution will look like some combination of e to the power of I kx plus b e to the power of, or basically just some sinusoids, right? A sine kx plus b cosine kx, right? And in this region, say region 2, your solution would look like some combination of growing and decaying exponentials, e to the power of say minus gamma x plus d e to the power of gamma x. Now if you impose the boundary condition that the wave function has to be 0 here, the cosine term has to be equal to 0, which is that b has to be 0. You can verify this for yourself. So basically the wave function is in this region 1 becomes a sine kx and the bx term is 0 right now, so this is just a sine kx. On the other hand, in the region 2, usually when we impose the fact that we want normalization to be the case, you would just say that this is 0 because this term blows up, and because of that you cannot achieve normalization. And so usually when you are solving a problem, we cannot take it to be 0. But instead what I want to do is not take that term as 0 and take this solution of the Schrodinger's equation and show to you that if we do this, we can actually achieve continuous energies in this bound states, and we'll show that only a subset of these bound states are normalizable, and those form basically the bound states and the discrete energies, right? So if we basically have this, then we have the wave function as e to the power of c times e to the power of minus gamma x plus d e to the power of gamma x, right? So basically we have this. After this, if we also impose the boundary condition here, basically your wave function would look something like this here, and then at this place it has to match the slope as well as the position of this. So basically here you will have some combination of say growing and decaying exponential that will cause it to either go below or above the axis. So basically when you impose the boundary condition, basically which is to say that let me use a different color. So if I impose the boundary condition, what I'll have to say is that say this length is 0 and L, so psi 1 at L must be equals to psi 2 at L, and the second condition is that psi 1 prime at L must be equals to psi 2 prime at L. I will not bore you with the details, but basically you get two different simultaneous equations, and using that you can solve C and D in terms of A, and basically you can get a solution that only depends on A and the values of K and so on. And basically the values of K we already know is given in terms of energies when you solve the Schrödinger's equation, right? So let me describe to you the features that we will observe, and in fact I will show you a simulation of the results that will help you understand this better. Basically, what we will obtain is that we have some kind of a solution of the Schrödinger's equation. So if I choose a particular energy, you would see that the solution would look something like this, and it will either go up or it will go down and so on. Okay, and if you increase the energy slightly, again you have a different wave function that will do something. Sorry, it would curve more, so it will do something like this, and again it will either go down or up, depending. It's going down or up actually basically is determined by the fact that when you have this wave function here, it hits this edge at a particular angle and at a particular place, and this angle and the particular place basically determines the boundary conditions, and hence will determine the combination of growing and decaying exponential, because you have C e to the power minus gamma x plus D e to the power gamma x here as the solution, right? So this slope that appears here, so the angle that it hits this boundary at and the position that it hits the boundary at will determine the values of C and D. So in most of the cases of all of the energies, if you look at all of these energies, they are all going to give you a valid solution of the Schrödinger's equation, but all of these continuous ranges of energies will produce a wave function where D is not equals to 0. So if D is not equal to 0, basically either what you will have is some kind of growing exponentials or decaying exponentials and so on, growing in the negative side if D is negative, right? So basically what will happen is that you will have wave functions that are diverging, so they are not normalizable. Now you will notice also, I'll show you the simulation to make this understanding a little bit more clear, but just visualize this with me here, which is that you will have a particular value of energy. Like let's say if you just decrease the energy a little bit, what will happen is your wave function will have a exponential that is going downwards and diverging downwards. On the other hand, if you go above, you will have a wave function that is diverging upwards. So basically in the middle there is a particular sweet spot energy where you have just the right angle at which the wave function hits the boundary, and so what you will have is that D will become equal to 0, and then you will have a decaying exponential here. So you will have a trail at infinity here, which is asymptotic, and that wave function is normalizable. So basically, if you impose the condition of normalizability on the solution of the Schrödinger's equation, what you have is you're basically choosing a subset of all of the continuous energies that are possible in this well, and only a subset of those energies are also satisfying this condition of normalizability. Hence you get this behavior of quantization. So let me show you a simulation to actually better understand this behavior. So here you see the small simulation. The purple and the blue curves represents the solution of the Schrödinger's equation without imposing the normalization condition, and you can see that the red line, which is representing the energy, can be continuously varied, and you can obtain a solution that is valid, and that is a valid solution of Schrödinger's equation which satisfies the boundary conditions as well, right? But you can see that most of these solutions have are diverging, right? Because of which they are not consistent with the requirement of normalizability. But I want to show you, for example, here
there is a particular energy where if I increase the energy, you see that wave function is diverging in the negative direction, while if I decrease the energy, the wave function is diverging in the positive direction. So there is a sweet spot energy where you'll have a trail at infinity, and you'll get a decaying exponential, and basically you'll have an asymptote at infinity. And in that case, you have basically a solution of the Schrodinger's equation, which is also normalizable. So basically, you can see that when you play around with this graph, there are multiple such points where this occurs, and so these all are basically a subset of all of the solutions of Schrodinger's equation, which also are consistent with normalizability, because without normalizability we cannot interpret the Schrodinger's equation as being a probability distribution function, as a valid probability distribution function. So we see that the normalizability condition basically restricts the space of all possible solutions of the Schrodinger's equation to only a subset of the solutions, right? Because of this, you are having this discreteness in the energy levels and all of the other dynamical properties. So yeah, this is why normalization in quantum mechanics leads to quantization.